In today's video lecture, we're going to finish the discussion of transient RLC circuits. We're going to start today's lecture with two examples that build upon the algorithm that we established in the last class. If you look at the circuit here, you have a resistor, a capacitor, and an inductor driven by a current source given by 10 U of t minus 3. And we're asked to find the voltage across the capacitor. The first thing we probably want to do is sketch what the input signal looks like. So Is of t, 10 U of t minus 3 basically is saying that the minus 3 is always present, and then at time 0, an additional 10 amps kicks in. So minus 3 plus 10 would be 7 amps. So in other words, this current source is 3 amps pointing down before time 0, and it immediately changes to 7 amps pointing up at time 0. So what we see is that there's a sudden change in the circuit at time 0, and because of that, we're going to get a transient response starting at time 0. The other thing that we're going to see is because the current source does not completely disappear at time 0, this is not a source-free circuit, but a driven circuit. So to solve this, the very first thing we want to do is find the voltage across the capacitor at 0 minus and the current through the inductor at 0 minus. So if you draw the circuit before the change in the circuit, we have a 2 ohm resistor. The inductor looks like a DC short. The capacitor looks like a DC open circuit. And the current source, as we said earlier, is 3 amps pointing down. So it's easy to see from this that the current through the inductor at 0 minus is 3 amps, which is also the current through the inductor at 0 plus. The voltage across the capacitor at 0 minus, from Ohm's law, we see that the 3 amps goes through a 2 ohm resistor, so we have 6 volts across it with the plus on the bottom and the minus on the top, 6 volts. So we see that Vc of 0 minus is negative 6 volts, which is also Vc at 0 plus. The next step is to redraw the circuit after the change in the circuit. So the circuit for t greater than or equal to 0, the resistor is unchanged. The inductor is now no longer a short. The capacitor is no longer an open circuit. And now the current source is 7 amps pointing up. And we see because of this current source here, it's now a driven circuit. So what we need to do is solve another DC steady-state problem. This is at infinity. Specifically, we need to find Vc at infinity. Why do we need to find Vc at infinity? Because what we're ultimately looking for is Vc. So at infinity, we once again have a capacitor open circuited, the inductor short circuited, but now because the current source is 7 amps going up, the voltage across this 2 ohm resistor is 14 volts with the plus on the top, and so Vc of infinity is plus 14 volts. The next step in the algorithm is to determine the differential equation associated with every single voltage and current in the circuit, and then find the characteristic polynomial, and from that get the form of the solution. There are two ways we could do that. One way is we could look back at the circuit here and start writing KVL and KCL equations to try to find the form of the differential equation. But that actually is not necessary. As mentioned earlier, we can use these canonical results to find the characteristic polynomial. So we could use canonical results to find the differential equation and ultimately the characteristic polynomial. The way to do that is to consider the source-free version of this circuit here. So the source-free equivalent is the following: a 2 ohm resistor, a 4 Henry inductor, and a 16/3 farad capacitor. Notice the current source we're ignoring because we're looking at the source-free equivalent. And what we see here is that we have a series RLC circuit. So from that we can immediately determine the differential equation. Differential equation should be VC double prime plus R over L times VC prime, so it's 1/2 VC prime, plus 1 over LC times VC, or 3/64 VC, is equal to some number. We actually don't care what this number is at this point because all we're interested in is the form of the characteristic polynomial. So the characteristic polynomial is s squared plus 1/2 s plus 3/64 is equal to 0. You find the roots. S equal minus 1/2 plus or minus the square root of 1/2 squared minus 4 times 3 over 64. All of that over 2. We get minus 3/8 and minus 1/8. I should point out once again that if you did not want to use these canonical results, you could start writing differential equations for this circuit and you would get this point. But why go through all that work when we have the canonical results that we could refer to? So we know the form of VC of t for t greater than or equal to 0 is going to be what? VC of infinity plus A1 e to the minus 3/8 t plus A2 e to the minus 1/8 t. One thing to note here, because this is a driven circuit, we have this additional term that we did not have in the source-free circuits. Another important point, we put that 14 in before we solve for the coefficients A1 and A2. And of course, since that is voltage across the capacitor, units should be volts. To find the coefficients A1 and A2, we next need to take the derivative of VC of t. So VC prime of t is going to be minus 3/8 A1 e to the minus 3/8 t minus 1/8 A2 e to the minus 1/8 t. To solve for A1 and A2, we need two initial conditions. Specifically, we need VC of 0 plus and we need VC prime of 0 plus. VC of 0 plus we know already from the previous page. It's minus 6 volts. VC prime of 0 plus we need to get from the second initial condition that we have, which is IL of 0 plus. How do we do that? If you look back here, you see that the current through this capacitor, IC, which in turn is C times dVc dt, is equal to what? It's the sum of IL plus this current here. So IC of t, which by definition is C times Vc prime of t, is equal to IL of t plus 7. So Vc prime of 0 plus, what we're looking for, is 1 over C times IL of 0 plus 7, which is going to be 3/16 times IL of 0 plus, which was 3 amps, plus 7, which is 30/16 or 15/8. We now have our two initial conditions. So we can solve for A1 and A2 by plugging in these initial conditions into the equation here and here. So let's do that next. Vc's 0 plus, which is minus 6 volts, has to equal 14 plus A1 times e to the 0 plus A2 times e to the 0. Or we get that A1 plus A2 is equal to minus 20. Vc prime of 0 plus, our second initial condition, the one that we derived, is 15/8, and it equals minus 3/8 A1 e to the 0 minus 1/8 A2 times e to the 0, or minus 3/8 A1 minus 1/8 A2 is equal to 15/8. We have two equations and two unknowns. One here, one here. We can use those to solve for A1 and A2. We see that A1 is equal to 5/2 and A2 is equal to minus 45/2. So we get that Vc of t for t greater than or 0 is 14 plus 5/2 e to the minus 3/8 t minus 45/2 times e to the minus 1/8 t. This again is for t greater than or equal to 0. Let's plot Vc of t now. So Vc of t for t less than 0 is going to be a constant, minus 6 volts. For t greater than or equal to 0, it's going to be 14 plus 5/2 e to the minus 3/8 t minus 45/2 e to the minus 1/8 t. So if you look at this response, it consists of a steady state value. It consists of a decaying exponential, with a time constant of 8/3 of a second. And another decaying exponential with a time constant of 8 seconds. What we see here is the second decaying exponential is going to be the dominant one for two different reasons. First off, it has a much longer time constant, so it takes longer to decay to 0. But in addition to that, its amplitude is much higher than the first one. And so what we're going to see is that this is the dominant decay term. So if you plot everything now, voltage across the capacitor starts at -6 volts. And by the way, if you plug in t equals 0, you get 14 plus 5 halves minus 45 halves, you get -6 volts. After a long time, both of these exponential decays go to 0 and we're left with 14 volts, as we know. And how long should it take to get there? It should take 5 times the second time constant, or 40 seconds. So it's going to take about 40 seconds for the voltage to move from -6 volts up to 14 volts. So this is the approximate shape of VC of t. You can't really tell from looking at this response that it is the sum of two different exponentials, but it is. Let's do a different example. This example is actually the most involved example in the entire EE210 class. It has many, many different steps. We'll go through them slowly so that we can see exactly how you can come up with the final solution. So a lot of stuff is going on in this circuit. First off, we have a voltage source that is being switched into the circuit at time 0. At the same time, we have a current source that's being switched out of the circuit at time 0. So this is going to be another driven circuit because it has sources present both before and after the change in the circuit at time 0. To make this problem even more complicated, we are not asked to find VC or IL, but we're asked to find a different variable, in this case IR. If you look back at the algorithm, this is one of those cases where you do have to worry about these additional steps here. One there, and one there. So that is what makes this problem so complicated, is it's driven and we're looking for a variable that is different from VC or IL. The first steps are the same. For t equals 0 minus, we're going to use to find initial conditions. So before the switches are moved, the voltage source is not present. So this 5 ohm resistor is just hanging. This 5 ohm resistor is here. The inductor is a DC short circuit. Since IL was not defined, we can define it however we want. We just need to be consistent once we define it. This 1 amp current source is present. The capacitor is a DC open circuit. Once again, VC is not predefined as a variable, so we can define it with whatever orientation we want. I will choose that one. Once we define it that way, though, we need to be consistent. And that becomes our circuit. And we have our other variable IR, which is ultimately the variable that we're looking for. Even though what we're looking for is IR, we still need to find both IL of 0 minus and VC of 0 minus because those are the two variables that will not change instantaneously. So IL of 0 minus, it's pretty easy to see. that the only currents flowing in this circuit are basically flowing through this loop here. So IL of 0 minus is -1 amp, which is also IL of 0 plus. VC of 0 minus, from Ohm's law, the voltage across the capacitor is the same as the voltage across a 1 amp source, is the same as the voltage across a 5 ohm resistor. Since you have 1 amp going through the 5 ohm resistor from top to bottom, you have 5 volts across that. So VC of 0 minus is 5 volts, which is also VC of 0 plus. In addition, we need to find IR of 0 minus. This is one of those added steps because what we're ultimately looking for is not VC or IL. IR of 0 minus, pretty easy to see, it's 1 amp, but I should point out that is not equal to IR of 0 plus. So you set those initial conditions aside. Now you redraw the circuit for t greater than or equal to 0. For t greater than or equal to 0, now this 12 volt source is present. You have a 5 ohm resistor. You have this 5 ohm resistor. The inductor is no longer a DC short. The capacitor is no longer an open circuit. And notice that this current source is now disconnected, so it's not there at all. And our variables VC, IL, and IR are defined as such. What we need to do here is make a decision. Because we're not asked to find VC or IL, but something else completely, we need to decide what we want to find in order to ultimately get IR. In other words, we're not going to solve for IR now. Instead, we're going to solve for either VC or IL as a function of time, and then at the very last step, find IR as a function of VC or IL. So we need to decide, looking at this circuit, whether it makes more sense to find VC or IL. A lot of times this just comes with experience, but sometimes it's pretty easy to see, well, a certain variable might be more closely tied in with either IL or VC. Here, it looks like IR is probably more closely tied in with IL. So what we're going to do is we're going to find an expression for IL of t for all time, and then from that, we're going to get IR of t. We could do this by solving for VC of t, but it seems that IL of t might be easier to convert to IR of t just because of the similarities between IR and IL. So the next step in the algorithm is for t approaching infinity, find IL of infinity. The inductor is a DC short. The capacitor is a DC open. 12 volts, 5 ohms, 5 ohms, IL, IR. IL of infinity is 0 amps because of the fact this capacitor is a DC open circuit. Note that we do not need to find VC of infinity or IR of infinity because we're solving for IL now. That's the only thing we need to know at infinity. However, it's not bad practice if we're ultimately looking for IR of t here. It's not bad practice to see what IR of infinity should be so that we can double check our answer at the end. So IR of infinity, looking at this circuit here, it's pretty easy to see that it's 12 volts over 10 ohms, which is 1.2 amps. Should point out again, it's not needed. This step is not needed. but it's good to check our final answer. We'll see that in a couple pages. The next thing we need to do is to find the form of the solution. So we'll do that on this page. To find the form of the solution, what we need is our characteristic polynomial, which we get from our differential equation, which we get from our canonical result. So for t greater than 0, we have a 12-volt source, a 5-ohm resistor there, 5-ohm resistor there, our inductor, our capacitor, and if you look at the algorithm, we look at the source-free equivalent. So if you set the source equal to 0, it's a voltage source equal to 0, it looks like that. We get that. Which in turn becomes a single resistor, which is 5 and 5 in parallel, or 2.5 ohms. Our inductor is 1/4 of a Henry, and our capacitor is 4/25 of a farad. So looking at the source-free equivalent, we now reduce our circuit to, in this case, a series RLC circuit. And by doing that, we can immediately read off the characteristic polynomial. Characteristic polynomial is what? S squared plus R over L times S plus 1 over LC is equal to 0, or S squared plus 10S plus 25 is equal to 0. Find the roots. Minus 10 plus or minus the square root of 10 squared minus 4 times 25 all over 2. We get repeated roots. So we know that IL of t, the current through the inductor, which is not what we're ultimately looking for, but we're going to find that first. So IL of t is IL of infinity, which we got there, it's 0 amps. So it's 0 plus B1 times e to the minus 5t plus B2 times t times e to the minus 5t. To solve for B1 and B2, we're going to need a second equation. That will be IL prime of t. So taking the derivative of that expression, we get the derivative of B1 e to the minus 5t is minus 5B1 times e to the minus 5t. The derivative of the second one is the derivative of t e to the minus 5t is first times the derivative of the second. So that's minus 5t times e to the minus 5t plus the second e to the minus 5t times the derivative of the first, which is just 1. All of that times B2. So we have two equations, one for IL of t, one for IL prime of t, and two unknowns, B1 and B2. So we need two initial conditions to solve for those. The two initial conditions that we need are IL of 0 plus and IL prime of 0 plus. The two initial conditions we have are IL of 0 plus and VC of 0 plus. So we have to find a way to convert VC to IL prime, because we know that IL of 0 plus from the previous page was minus 1 amp. VC of 0 plus, we know from the previous page, is 5 volts. So how can we find IL prime of 0 plus? Well, let's look back at this circuit. We'll draw it yet again. For t greater than 0, we have the following. Where IL was defined as that current, IR was defined as that current, VC was defined as that voltage, so IC would be defined as that current using the passive sign convention. So what we need to do now is try to find an expression for IL prime of t. What we know is that IL prime of t is VL of t over L. Why? Because the voltage across the inductor is L times the derivative of the current through the inductor. But let's think about VL of t. VL of t is given by that, and notice because IL is defined as a current from left to right, using the passive sign convention, the VL has to have the plus on the left. So even though it was arbitrary that we defined IL as going left to right, once we define IL that way, it fixes how VL has to be defined. Let's do a KVL along that loop. We get minus 12 plus 5 times the current through that resistor. But the current through that resistor is just IR plus IL. This current branches down into that current plus that current. Plus the voltage across the inductor, VL, that's what we're solving for, plus the voltage across the capacitor, VC, is equal to 0. But we can express IR differently. The current through that resistor is the voltage across that resistor divided by its resistance. But the voltage across this resistor is the same as the voltage across the inductor and capacitor put together. So IR is equal to VL plus VC over 5 ohms. So we now get that minus 12 plus 5 times IL plus VL plus VC over 5 plus VL plus VC is equal to 0. Let's put VL to the left-hand side and everything else to the right-hand side. We get VL times 2 is equal to 12 minus 5 times IL minus 2 times VC, or VL is 6 minus 5 halves IL minus VC. So VL of 0 plus is 6 minus 5 halves of IL of 0 plus minus VC of 0 plus. But we know what IL of 0 plus is. It's minus 1 amp. We know what VC of 0 plus is. It's 5 volts. That's minus 1. That's plus 5. So we end up getting 7 halves of a volt. Finally, IL prime of 0 plus is VL of 0 plus all over L, which is going to be 7/2 of a volt divided by 1/4 of a Henry, or 14. So all of this work on here was just to find the second initial condition. As I mentioned, this is the hardest step typically in these transient RLC circuits. So we can now get our B1 and B2 coefficients. Specifically, we know that IL of 0 plus, which is -1, should be B1 times e to the 0 plus B2 times 0 times e to the 0. So from this, we directly get that B1 is equal to -1. From our second initial condition, IL prime of 0 plus, which is 14, has to equal this expression, plugging in t equals 0. So that equals -5 B1 e to the 0 plus B2 times -5 times 0 times e to the 0 plus 1 times e to the 0. You solve this, you get B2 is equal to 9. So IL of t is now -1 e to the -5t plus 9 times t times e to the -5t amps. Guess what? We're still not done, because we still need not IL of t, but IR of t. So let's go back to this circuit. For t greater than 0, once again, IR is defined as that current, 5 ohm resistor, 5 ohm resistor. IL is defined as that current. Let's do KCL at this node here. Let's call that VR. Let's call this ground here. And let's do KCL here. Our goal is to find an expression for IR in terms of IL. If you do KCL at this node, we get VR minus 12 over 5, that is that current, plus VR over 5, that is that current, plus the current to the right, it's just IL, is equal to 0. Solving for VR, you get that VR is equal to 6 minus 2.5 times IL. But what's IR? IR from Ohm's law is just VR over 5 ohms, so it is going to be 1.2 minus IL over 2. So we can use this expression here and this result here to find a final expression for IR of t. So what does IR of t equal? Well, we knew from a very early step, which seemed like ages ago, that IR of 0 minus was 1 amp. Once again, remember that is not necessarily IR of 0 plus. So we get 1 amp for t less than 0. For t greater than 0, it's 1.2 amps minus IL over 2. So it's going to be 1.2 amps minus IL over 2. So instead of having a -1 and a +9, we're going to have a +1/2 and -4.5. So plus 0.5 e to the -5t minus 4.5t e to the -5t amps. And this is valid for t greater than or equal to 0. Note, IR of infinity is 1.2 amps. If you remember, back here, we solve for it explicitly, and I said we didn't need to do it, but it's a good idea because you can check your answer later, and that's exactly what we did. So even though we did not need to solve for this here, we can verify that sure enough, our final equation for IR of t gives us the same final value as t goes to infinity. Finally, we can plot everything. For t less than 0, IR of t was 1 amp. At t equals 0 plus, if you plug in 0 plus into this expression here, IR of 0 plus is 1.2 plus 0.5 e to the 0 minus 4.5 times 0 times e to the 0, or 1.7 amps. So the value at 0 plus is 1.7. The value at infinity is going to be 1.2, which is going to be here. So eventually it's going to end up at 1.2. How long is it going to take to do that? Well, the time constant looks like it's 1/5 of a second, so it's going to take about 1 second. And what's going to happen in between? It's actually going to go down and then migrate back up to 1.2. And this point happens about 0.3 seconds. You could find out exactly where it happened by taking the derivative of IR of t and setting it equal to 0. But the important thing to note is, first off, the value at 0 minus was 1 amp. At 0 plus, it immediately jumps to 1.7, so there is a sudden change in IR of t. Remember, there cannot be a sudden change in IL of t, but there can be a sudden change in IR of t. So as t progresses, it actually drops below 1 amp, turns around and comes back up, and eventually settles at 1.2 amps. As I said, this is a very long, complicated problem. This is definitely the longest problem in EE 210. But if you break it down into the individual parts, finding DC steady state values at 0 minus, finding steady state values at infinity, finding the form of the characteristic equation, finding the roots of the characteristic equation, from that finding the form of the solution, then finding your second initial condition, which we did here, and finally using that to find B1 and B2, and at the very end, because we're not asked to find IL or VC, but IR, at the very end, finding this general expression relating IR to IL, we can get our ultimate answer, which is here. One last thing I want to point with this example, way back here, we decided to solve for IL of t. We did not need to solve for IL of t there. If we wanted to, we could have solved for VC of t. All of these steps would have been the same except for our initial conditions. Rather than being IL and IL prime, they would have been VC and VC prime. So our B1 and B2 would have been different. And then this expression here would be different. Instead of finding IR in terms of IL, we'd have to find IR in terms of VC. The final answer for IR of t would be the same. So what you may want to do on your own is see if you can repeat this example, but instead of finding IL and using that to find IR, find VC and use that to find IR. In the last topic in this note packet, we're going to talk about lossless LC circuits. LC circuits are a special class of RLC circuits in which there is no resistor. Without a resistor to dissipate the stored energy in the capacitor and the inductor, the circuit just continues on forever. And we're going to see that it actually continues with the sinusoidal oscillation. So these lossless LC circuits are also called resonant circuits or oscillator circuits. So imagine an LC circuit where the inductor has some initial current IL0, which means that there's energy stored in the inductor in the magnetic field, and the capacitor has some voltage VC0, which means the capacitor is storing some energy in the electric field. The voltage across the capacitor and the current through the inductor are going to cause currents to flow through the circuit. What's going to happen though, without any resistor present, the energy stored in the capacitor and the inductor are just going to be transferred back and forth, and you're going to get a sinusoidal oscillation. We can look at the math behind these lossless LC circuits by considering the underdamped RLC circuit case. In the underdamped case, if you remember, you get a sinusoid with an exponential decay envelope. And the amount of decay is determined by this term alpha, which was R over 2L. But in this case, the resistance in the RLC circuit is 0. It's basically having a series resistance of 0. If alpha is 0, then e to the 0 is just 1. Furthermore, the frequency of oscillation omega sub d, which is given by this expression here, reduces to this expression, which is what we call resonant frequency. We use the term omega naught to represent resonant frequency, and notice it is a function only of the inductor and capacitor value. So the response now becomes what's called an undamped response. And we see that the voltage across the capacitor is a cosine and a sine of the resonant frequency added together, which can be recombined into a single sinusoid of amplitude A and angle phi. To determine the amplitude A and phase angle phi of this oscillation, we have to utilize the two initial conditions, as we'll see on the next page. So using the two initial conditions, the voltage across the capacitor and the current through the inductor, we can then find equations for A and phi. I'm not going to go over the details here, but the results are down here. Notice that A and phi each depend on the value of the inductor, the value of the capacitor, and the initial conditions for the inductor and the capacitor. And of course, the other equation from the previous page that we need, omega naught, is just 1 over the square root of L times C. These three equations are all we really need to solve these lossless LC circuits. Before we get into an example, let's talk a little bit about this exchange of energy. So as you know, the inductor stores energy in its magnetic field, and it's a function of the current through the inductor. And the capacitor stores energy in its electric field, and it's a function of the voltage across the capacitor. So what happens then, if the inductor current varies sinusoidally, that also means the capacitor current varies sinusoidally with the opposite sign. That's because the capacitor current is defined as the current going down there, which is opposite the direction of IL. Voltages, on the other hand, because we define the voltage across the inductor is that, using the passive sign convention, the voltages across the capacitor and the inductor are the same, and so there's only one voltage signal. If you think about the power instantaneous power absorbed by the capacitor and the inductor is just voltage times current. And so for the inductor, we end up with this waveform here. And with the capacitor, we end up with this waveform down here. Notice that the power sinusoid has twice the frequency of the voltage and current sinusoids. Energy, of course, is just the integral of the power. So if you integrate the two power signals on the left, you get the energy for the inductor and the capacitor. A couple points we should make here. First off, notice that the stored energy is always positive. That makes sense. You can't store negative energy. Second thing you note is that when the energy stored in the capacitor is a maximum, here, here, and here, the energy stored in the inductor is 0. Likewise, when the energy in the inductor is maximum, the energy stored in the capacitor is 0. In other words, there are some points in time where all the energy is stored in the capacitor. There are other points in time when all the energy is stored in the inductor. Another thing to note is when the energy in the inductor is maximum, these are the red points, that is when the current through the inductor has the biggest amplitude, whether it's positive or negative. Likewise, when the energy in the capacitor is maximum, that happens when the voltage is maximum. So maximum voltage corresponds to maximum capacitor energy, and maximum current corresponds to maximum inductor energy. But an interesting result is the total energy, which is the sum of the inductor energy and the capacitor energy itself, is constant. In other words, all that's happening during this oscillation is the energy keeps on going back and forth between the capacitor and the inductor. At some points in time, all the energy is stored in the capacitor, there, there, and there. At other points in time, all the energy is stored in the inductor, here, here, here. And at other points in time, the energy is stored in both the capacitor and the inductor. But the total energy is always constant. Once again, this makes sense because there's no resistor to dissipate the energy, and the capacitors and inductors themselves do not dissipate energy. They just store it temporarily and then release it back to the circuit. With those preliminaries done, we can now do a couple simple examples with lossless LC circuits. So in this problem, we're given an 8 microhenry inductor and a 2 microfarad capacitor. We know that the initial current in the inductor is 3 amps and the initial voltage across the capacitor is 8 volts. How these got to this point doesn't matter. We're assuming that at some time before 0, there were voltage and current sources present to energize the inductor and charge the capacitor. And then at some time, let's call it 0, those are removed, and that this energy is now in this circuit and ready to get transferred between the capacitor and the inductor. So the first thing we know is the voltage across the capacitor is going to be what? Some constant A cosine omega naught t plus phi. We have our 3 equations that we can now use to find A, omega naught, and phi. Omega naught's the easiest. It's a function only of L and C. Specifically, it's 1 over the square root of L and C. Work out the math. It's 250,000 radians per second. Notice this is the frequency in radians per second, not the frequency in hertz. A is the square root of VC naught squared plus L over C times I L naught squared. So notice the amplitude is not only a function of the capacitor and inductor values, but also a function of the initial voltage across the capacitor and the initial current through the inductor. You plug in the values for all of these variables, and you get 10 volts. Finally, phi is the inverse tangent of the square root of L over C times the initial inductor current divided by the initial capacitor voltage. This one ends up being 36.9 degrees. One warning when you use this inverse tangent equation, on your calculator you need to make sure of whether you were in radian mode or degree mode and record this accordingly. So putting these together, we know the voltage across the capacitor is 10 cosine 250,000 T plus 36.9 degree volts. To find the current through the inductor, we use the fact that the current through the inductor is negative the current through the capacitor, which in turn is equal to minus C times dVc dt. So taking the derivative of the voltage expression and multiplying it by negative C, we get 5 sine 250,000 T plus 36.9 degrees amps. Notice the voltage and current are always going to be 90 degrees apart. One's going to be a sine, one's going to be a cosine. And we saw that comparing this figure and those figures. They are 90 degrees apart. Let's look at the energy. The total energy at time 0 is a sum of the energy in the inductor at time 0 plus the energy stored in the capacitor at time 0. The energy in the inductor is 1/2 times the inductor value times the initial current squared, happens to be 36 microjoules. The initial energy in the capacitor is 1/2 times the capacitor value times the initial voltage across the capacitor squared, happens to be 64 microjoules. So the total initial energy is 100 microjoules. As we stated though, this initial energy is not going to go anywhere, which means the energy at any time has to also be 100 microjoules, which we can also see by finding an expression for the energy as a function of time. The energy as a function of time is going to be 1/2 times the inductor value times the current through the inductor squared plus 1/2 times the capacitor value times the voltage across the capacitor squared. So we get 1/2 times 8 times 10 to the minus 6. The current through the inductor is 5 sine 250,000 T plus 36.9 degrees squared. Energy due to the capacitor is 1/2 times the capacitor value times the voltage across the capacitor squared. You work out this math, you get 100 times 10 to the minus 6 times cosine squared 250,000 T plus 36.9 plus sine squared 250,000 T plus 36.9 degrees. But cosine squared x plus sine squared x always equals 1, and what we see is that the total energy is constant even though the energy stored in the inductor varies with time and the energy stored in the capacitor varies with time. And this is once again exactly what we saw in these figures here. The inductor energy is sinusoidal. The capacitor energy is sinusoidal, but the total energy is constant. Let's look at one last example. This is one of those backwards type examples where we give a couple figures and have to work backwards to determine circuit components. So we are given a plot of the current through the inductor, and notice it has a maximum current of 0.25 amps, and we're given the voltage across the capacitor with the maximum voltage of 0.5 volts. Furthermore, we see that the period is 6.28 seconds, which happens to be 2 pi seconds. So how can we use this information to determine the values of the inductor and the capacitor? Well, if you recall, the frequency of oscillation is 1 over the square root of LC. But the frequency of oscillation is also 2 pi over the period. Since the period itself is 2 pi, we get the relationship that 1 over the square root of LC equals 1, which implies that LC equals 1. So where do we get the rest of the information we need in order to determine what L and C are? We know that when the voltage is maximum, all the energy is stored in the capacitor. So the capacitor stores all the energy when the voltage is maximum. And what is the energy stored? It's 1/2 times the capacitor value times the voltage across the capacitor, which is 0.5 volts squared. We also know that the inductor stores all the energy when the current is maximum. And that energy is 1/2 times L times 0.25 squared, which we get from there. These two energies have to be the same. So we end up getting the 1/2 C times 0.5 squared has to equal 1/2 L times 0.25 squared. You work out this math, you get that L has to be 4C. At the same time, we know that LC has to equal 1, so we get 4C times C has to equal 1, or C squared is 1/4, or C is 1/2 of a farad. We can plug that into this equation then to get that L is 2 henries. So we get our final answer. The capacitor value is 1/2 of a farad, and the inductor value is 2 henries. And where do we get this from? We get it from the period of oscillation, and then the maximum current, and the maximum voltage, and the energy relationships. So this ends this packet of notes and ends this very brief topic on lossless LC circuits. Have a good day.